Next big honor is introducing Michael Jordan. He's a professor at the University of California, Berkeley. Before Berkeley, he was a professor at MIT. His research accomplishment span computational, statistical, biological, and economic fields. He is most known for his work on variational methods for statistical inference and continuous optimization, but he worked on lots of stuff, probabilistic models with applications to problems in computational biology, information retrieval, signal processing. He was building connections between these areas that deeply enriched both machine learning as well as the other areas that he connected to. He worked on a huge range of areas: distributed systems, machine learning, optimization, optimal control, multi-arm bandits, matching markets, and I'm sure I left out some. He's graduated close to 100 students, and looking at his list of students is really who is who in machine learning. Like almost everyone, or a huge number of influential machine learning were Michael Jordan students. In the last, I think 5+ years, but he can correct me if I'm wrong, he got very interested in the interaction between incentives and learning, and given our interest in incentives and learning, I really appreciated this change of focus. He's been incredibly distinguished, member of the National Academy of Sciences, National Academy of Engineering, American Academy of Arts and Sciences. He has a huge number of awards, including the IEEE Newman Medal, the Research Excellence Award, ACM Alan Newman Award, and World Laureate Association Prize. I guess on a personal note, as I already said, I really appreciated his turning to the right side and understanding the importance of incentive the last many years, but I've been admired him as a source of advice on machine learning way before that. And thank you, Michael. And today he's going to talk to us about contracts, uncertainty, and incentives in statistical decision making. And the slides are up. So.
I want to thank Ava and Francesca for inviting me. In fact, on a personal note, I first heard about algorithmic game theory. I think it was from a talk from Ava maybe 10 or 15 years ago. And it definitely attracted my attention. It was different from what else I had seen. It was computer science, but for problems in the real world. And so I thought maybe I should work on that. And I didn't at that time, and now I am. And part of the problem was I always like to know what's my real world application I'm targeting. And I really kind of want to make the world a better place. And so most of the talks problematically for me that I saw we're going to make Google richer, that we're going to do ads. It was all about ads and auctions for ads and online auctions and all. And that kind of got solved, and that was great. But now we're in another era where Google's not necessarily the good guys. In fact, I gather they're a monopoly now. It's been decided, and thanks, Susan, for that. And I saw the talks here, and they all had a lot of AGD theory, but all the problems were not about ads. And so I think we're now kind of arriving at all the other problems we can work on to make social welfare large with our methods, and think about all the externalities that our methods are having, the bad ones out there. And so that's what my talk is really going to be about. There's two of these. Let me see if I can find one that works. There we go. So the other part of my history was that around that, about 10 years before that, I'd gone to Amazon and spent time there. And I saw the precursor of what's called large language models now. And it wasn't about language, it was about supply chains. But it was almost the same scale that we're seeing now. And what alarmed me about it was, first of all, it was really good, but also the uncertainty quantification was terrible. All right? And I think that's still true to this day. So that's what I did the last, in that intervening 10 years. I didn't do AGT. I said, I'm going to work on uncertainty quantification. And I'm a statistician kind of at heart, even though a lot of computer science in me. And I don't believe Gaussians, and I don't believe asymptotic uncertainty and all that. I didn't believe the kind of methodology I was seeing out there being used, and I didn't believe it was going to work at the scale that I was, about ready to see. The brute force AI was not going to be able to use those kind of that way of thinking. All right, so let me just sort of say I think that's really a huge problem right now. It's an elephant in the room. There are wonderful things about large language models and ChatGPT and all, but if you ask ChatGPT, how sure are you about what you just said? It's really going to make something up. Okay, it's going to say, well, I'm really sure, or I'm not sure. That's because in the data, some human said I'm not sure in some contexts like that. That's terrible uncertainty quantification. That's not reasoning about uncertainty at all. Okay? And even maybe more quantitative about it, can't do that. So I don't want to interact with systems that can't talk about their uncertainty and be honest about it and interact with me. And that's what humans do so well. In fact, I think that's probably one of the most human endeavors, is to be unsure and to get information from others and to do well in collectives. All right? And so that's completely missing, okay, weirdly. Okay, so I don't like this whole AI paradigm. I really hate the McCarthy paradigm, the Turing paradigm of let's make artificial humans. I don't like the Frankenstein side of it. And it's really because that's not where I think intelligence mostly accrues, is in the individual human who's doing math problems. Yeah, there's a lot of amazing intelligence there, but in mimicking that, I don't want to do it. I want to let humans do the math. I want to think about collectives and new kinds of collectives and new kinds of intelligence that could arise at the collective level and all the problems that are going to arise there. I want to think about those. Now, for this community, I don't think that's a big deal. But, as you all probably know, out in the real world, the Silicon Valley is full of people who don't think that way. And it's terrible. They really think about this Frankenstein kind of model. So it's time to fight back. So I think that, again, I think same problem Susan was having. Okay, so it's about the collective. Now, uncertainty has two main flavors, I'm going to argue. One is the kind I'm used to as a statistician, that you didn't collect enough data. Uncertainty goes down as 1 over square root of n if you do it right. You can sample it away. The other kind of uncertainty is the more economic kind, if it's about information asymmetry. If I've got a principal and an agent interacting with each other and their strategic goals that they have, they're not going to just give the information away. In fact, they're going to very much use it privately so they get strategic advantage. And that's not going to go away from sampling. It's a form of uncertainty. Absolutely, I'm uncertain about what that other person knows, but it's not going to go away by me sampling. Okay, and so that's a real gap between two fields that have been both talking about uncertainty, but in very different ways. So we really want to put these two things together. The other point I want to make is this whole business about AI. First of all, it was never called AI. It was called machine learning for all these years. And it really didn't start with large language models at all, but it started with the same technology about 20 years before that, for now. And so I'm thinking about circa 2000, Amazon was building supply chain modeling for very large-scale logistics problems. They can now serve about 1 billion products to hundreds of millions of people. Each one of those billion products is formed of little parts, and they had to be put together all around the world and shipped over ships and containers and boats and so on. And so the supply chain is the world's largest stochastic control system. Nothing like this had ever been done before in history, and it's huge. And so how was that done? Definitely not by humans sitting down and writing out things on pieces of paper. So it was done by using machine learning algorithms, and they didn't think neural nets were the thing to use in the day. It was random forests. So they built huge infrastructure to do random forests, and they couldn't do it on one machine because they had so much data. So they started to build tens of thousands of computers to do it. Okay? And that was in circa 2000. And they did it so well that it really worked. I went down there and I was curious about this, and I saw it working. And it was coming, the logistics people were saying, in our OR textbooks, there's nothing like it. It's coming up with new solutions we've never seen before. Very creative. All right, it's already a glimmer of what we're seeing now. It can do creative things, right? It had vast amounts of data, all right? But the uncertainty quantification was terrible, okay? But it didn't really somehow matter for their kind of problems. Now, we didn't talk about it in the New York Times. Well, why? Because it was on the back end. Come through second and third generation, the next generation was the same architecture, random forests on what became called the cloud at that point. This was the beginning of the cloud. The cloud was built by Amazon to do random forests on supply chain data. Never talked about, but that's the truth. Next phase was, let's use transactional data. Humans come into the picture now, not just about back end. So now it becomes recommendation systems. Same company, same infrastructure, same everything. And very interesting. Nothing appeared in the New York Times about it. The next phase, everything is roughly the same, except maybe neural nets instead of random forests because they have some advantages. But now it's human-produced data, it's speech and language. Okay? But it's gradient descent methods, it's in the cloud, now GPUs have come into the mix, but it's pretty much the same, and now it's all over the New York Times and it's all over Silicon Valley. I don't think that's where we're stopping them. I think what's really happening in this area is not the supercomputer, superhuman in the computer, the Sam Altman dream. It's really emerging markets at planetary scale involving data flows and humans and uncertainties of all kinds for particular purposes like healthcare and transportation and so on and so forth. So again, in this community, I don't probably have to emphasize that, but if you're arguing with people out there in Silicon Valley or about the AI thing, this is kind of a perspective you might want to take. This is a real history of how this arose. And why did it get called AI at some point? Because it was definitely not old-fashioned AI that led to all this. It was machine learning. It was just PR. And I think it was Google, frankly, that decided, let's call it, machine learning is not good enough, let's use this old term AI. All right, so now that's in the real world, which I think is the most important thing. What about the academics? And as Eva kind of alluded to, algorithmic game theory was a thing at some point. And the way I like to think about it is that there's three traditions that are relevant in this conversation in academia. One is inferential thinking or statistics. Another is computational thinking. That became a buzzword at some point, computer science. And the other is what we might call incentive-theoretic thinking, economics. And they have very good, strong bipartite connections. All right, but what's missing from each of those bipartite is the third leg. Okay, so if you go to machine learning, which is just statistics meets computer science, that's really what it is, and you say, is there much economics in it? And the short answer is almost none. Okay, now there is exceptions to everything I'm going to say right now. There's some old game theorists who came in, and there's some, but not much. If you look at econometrics, God bless, there's a lot of great statistics and there's a lot of economics. It really is sophisticated on both of those, but not a lot of algorithmic scalability issues. Not a lot of algorithms of the kind that I at least recognize. And then lastly, if you look at algorithmic game theory, again, exciting, mostly auction focused for a long, long time, hardly any statistics, not much data. All right, and so the important point I'm making is that if you go to the real world, like Amazon, you sit down and solve real problems, there'll be all those traditions around the table. Usually an operations research person who's been trained on all of them, or maybe a chemical engineer who happens to know all of them, but anyway, all three of them are on the table. In academia, however, rarely are all three of them ever together. In a conference, they never are, except something like this. Okay, so finally, what kind of real problems do I want to work on that aren't, say, just ads? So here's an example. Alireza Falah is in the audience, and this is joint work with Alireza and others. I'm going to return to this project at the end of the talk. This is a nice example of now data markets. So data is not just something that is used to drive the algorithms. It's something that's a good. It's an economic good. So people have worked on data markets. This is an interesting three-layer one. So we have on the left a user, and we have in the middle the platforms, and then we have data buyers. So the user is interacting with platforms. Take MasterCard as an example, and they send data. They effectively send data to MasterCard, who provides a service back in return. More data that MasterCard gets, the happier they can provide a better service. On the other hand, MasterCard does not make that much money from just their core business, so they sell some data to third parties who use that to do data analytics, market design, and advertising. And so money flows in all these directions, all right? Now, people care about their privacy, and so they don't really want to have all this data flowing across to the buyers. And so they would like to ask the platforms, give me a privacy guarantee. Add noise to the data at some level and tell me what that level is. Do differential privacy. Okay, so the platforms kind of have to do that to be in this market. All right, if they start doing that, however, they damage the data from the point of view of the data buyer. The data buyer is going to give them less money. On the other hand, they're going to get more users because the users are attracted by that nice privacy guarantee, so they'll therefore get more data so they can build a better service, and they have more data, they can send more data to the data buyer. So it's an interesting set of locked incentive structure here. And it's really principal-agent paradigm, but it's a little bit different in that the platforms are both a principal and an agent simultaneously. Okay? So anyway, I'm going to go through this problem a little bit and show you some of the equilibria that emerge and in the context of data, all right? And we even talk about regulatory recommendations using this kind of analysis. All right, so that's one example of a real-world problem. Here's my other really favorite example. I've been doing this for about 10 years. I'm also a musician, and I have a friend named Steve Stout, who's a legendary hip-hop producer in the United States. And I've been involved in this company called United Masters. It's about 7 years old now. I was the original scientific advisor. I'm now actually on the board. And the short version of this story is that there's, information technology has allowed music to be sent everywhere, and everyone is making it and listening to it, but there's no good market for it. The young people who are mostly between 16 and 25 making music aren't making any money. okay? They're giving a little handout from, other, streaming services, but it's not a real viable market, and they can't have a job. They do it for a while, they get out and they do something else. It's really broken, and it's amazingly because everyone wants to listen to music. All right, so United Masters is a three-way market, and briefly, it's got producers, who are the people making the music, that are typically between 16 and 20. There are now 3 million of them signed up on the United Masters platform, okay? So this is a really working thing. There are listeners, huge numbers, and there are brands critically. And then brands include, these aren't just made-up brands. The NBA, the NFL, FIFA, State Farm have all signed on. They're taking their music now from United Masters. When they have to do syncing, here's a clip, here's a video, the NBA shows a video, and behind it there's music. That's now United Masters artists. In that moment, the artist gets paid, okay? And they see how much they got paid. The other brands see that that artist is liked in that demographic, and they reach out to the artist and say, you want to do some songs with us? That's all happening right in this moment. So there now are tens of thousands of people who are making salaries off of this, and that's going to grow. Real salaries. And I don't mean billions like Beyonce, but they're making $100,000 a year or $50,000 a year. All right? And now what's behind all this? This is what I would call AI. This is an intelligent working system. It takes in data, it does market design, it's all adaptive, there's no regret algorithms, there's incentives all built in, and it's scaling and seems to be working and all that. Okay? So this is the kind of problem I really am excited by to work on in the real world. And how do we work on those problems? Well, there's lots of things behind the scenes here. We've got to work on optima and equilibria for sure, but mostly dynamics, because this system is never in equilibrium. And moreover, there's all kinds of nonlinearities and all kinds of saddle points of the kinds we're really used to in optimization, and we have great ideas about how to solve. All those problems arise here, and we're solving them in this more general setting. So the rest of the bullets on the slide are things that you'll all recognize, uncertainty quantification, information asymmetry, and so on. And then bias is a really important word. That came up in Avram's talk earlier, and I want to emphasize how important it is because we're all used to small problems where there's variance that has to be controlled, but as I allude to in these really big emerging systems, it's really bias, which really kills you. Okay, so I want to emphasize that, and I'm going to take a couple of these little vignettes, depending on the time I have, and dig into them. This is the last talk of the day. I'm going to not show lots of derivations, but I will show some theorems. Okay? So let me start with this bias mitigation thing. So this is a project that doesn't have as much econ in it as some of the later projects are going to have. There's not incentives in this one, but I think it's an important project because it really gets at bias mitigation in a way a statistician thinks about it. All right, so I think this audience is mostly econ and some CS and less statistics, so I'm going to emphasize my statistician heart here and tell you about kind of how statisticians think about bias. All right, so this is a joint with my statistician colleagues. Anastasia is a student with me, and Tiana was a student. She's now at Stanford. Stephen is now at MIT, and Clara is at Genentech. All right, so the setting here is kind of large language models, but the AlphaFold version of it, so generative AI, if you will. These things can generate hundreds of millions of structures of proteins from sequence, okay? Hundreds of millions. We never had anything like this before. In the lab, we are now up to hundreds of thousands of crystal structures that are known. Very expensive and slow. All right, so people are saying, well, why can't we use the generative AI data as data and replace the lab data? Because it's so accurate. Why don't we just do experiments with AlphaFold instead of having to go to the lab and spend all the time and effort? Okay? Here's an example of that. In 2004, there was an important study done where people were studying quantum disorder in proteins. So most proteins like to fold up, as you probably all know, but occasionally there's some quantum fluctuations that make strings kind of hang off. And that used to be thought of as a broken protein. And it was realized then that you could put multiple of these proteins together, and those strings would kind of tend to do a little bit of hydrogen bonding. And if you put them in a grid, you could make grids that were adaptive. And if you put them in membranes, that could let things in and out of the cell. And it turns out that biology discovered this billions of years ago. Okay, so it's actually an important part of biology that wasn't known. These people were prescient in trying to study that, so they did a little hypothesis test. They looked over the entire protein data bank, and they said, quantum disorder, yes or no? Phosphorylation, yes or no? It's an active protein. So it's a little 2x2 table, and they just do a hypothesis test with the odds ratio. Now, how much data did they have? Well, they had 10,000 entries in the protein data bank. So some, big data, but not huge. Anyway, sadly, they got their odds ratio, they got a confidence interval, and it covered 1. 1 means there's no effect. The ratio is 1. So they said, well, we can't conclude anything. People kept trying. And so 20 years later, someone said, well, look, let's just use AlphaFold instead of actually using lab data. Because AlphaFold is so accurate, it's more accurate than any human, it's more accurate than anything we had before. Why don't we just use it to produce the data for this? So let's calculate that little 2x2 table again, get our odds ratio, get a confidence interval, see if it covers 1 or not, and make a decision. And we'll get a Nobel Prize. All right, now is this a good thing or a bad thing? Okay, overall I think it's a good thing. This generative AI can be used in this way. All right, but actually, somewhat shockingly, it's a really bad thing for this problem and for lots of other problems. Okay, and I'm going to show you that on the next slide or soon. Just before I do that, here's sort of we took a week of papers in Science and Nature that were doing things like this, and they're just all over the place. It's now called AI for science or something like that, some buzzword, where you take generative AI and it generates data. Here is the problem. Okay, so I'm going to take a moment on this slide. The x-axis there is the odds ratio. So if it is 1, there's no effect. The ratio is the same with the quantum disorder or not. If it's bigger than 1, you have an effect. The little regions there are confidence intervals, and we held out half the data. We redid the whole experiment that had been done. Hold out half the data and do a Monte Carlo on that to get a gold standard. Okay? And then just kept that data to the side and redid the entire experiment on the other half of the data. The dotted line is the Monte Carlo estimate. Okay? So let's call it the gold standard. The gold region there is the confidence interval coming from using AlphaFold and making your 2x2 table and just doing statistics on AlphaFold. And you can see it's a very small confidence interval because you have a huge amount of data. All right? You're very sure of yourself, but you're not covering the truth. All right? So it looks ad hoc, it looks good. Run with it. Why not? Well, because it's not covering the truth. So there's something wrong here. All right, so the statistician might just say, well, forget that was a dumb idea. Just go and see how much data you really have. Now we don't have 10,000, we have 100,000 in the protein data bank. It's grown. Use the 100,000 and see what you get. That's the gray region. So the confidence interval is still very large, even with 100,000 data points. It's a complicated phenomenon, and it still covers 1. You can't make a decision. So long story short, we have a new method, we call it prediction-powered inference, which is a bias correction procedure for confidence intervals. Okay? And it makes no assumptions, it doesn't model the bias in any way. It makes no assumptions of the form of the bias. So as a statistician, that's what I want. I don't want to have to model the bias. All right? And it does that non-parametrically, and it'll deliver a confidence interval, that's the green region, which provably covers the truth. Okay? And it is generally much smaller than the statistical confidence interval that doesn't use AlphaFold or the machine learning help. All right, so I'm going to show you a little bit about how we do that, but just first of all, why is this happening? Isn't AlphaFold extremely good? Why is it giving such a terrible confidence interval? And here's the reason. At post hoc, we looked at the data, and here's an example. Here's an AlphaFold prediction on the left of a certain protein. On the right is the actual experimental structure. You can see there's quantum disorder. All right, so it really botched this protein. We found that over a lot of the proteins with quantum disorder. Why is this happening? Well, because AlphaFold is trained on all the past data that people have collected in the past for all their past scientific hypotheses. Scientists are rarely interested in testing hypotheses on the past data. They're interested to be on the edge of science. All right, and so they're looking at phenomena that haven't been actually well characterized in the data, and this is a good example. All right, so you're going to make big bias errors because you're looking at things that don't have a lot of actual data, even though the overall system accuracy is extremely high. It's going to be extremely low on the things you probably care the most about. All right, that's why it's happening. So we did this, and there's a paper in Science, and in that paper we did experiments for 10 different domains, some astronomy problems, some ecology problems, some other problems, and it happened again and again and again. Here's a problem with gene expression. I don't want to get into details, but on the right, lower right there, you can see the same phenomenon happening with a small confidence interval with the machine learning method, a big one with the statistical, don't use machine learning, and the intermediate one with our new method. This is my favorite example. This is a problem using data from the California census. There's a machine learning model that was used, and it gave a tiny confidence interval there. You can see that little gold region. If you didn't know that the gold standard was already over here, you'd say, this is a fantastic result. You're extremely sure of yourself, all right? But you're dead wrong. You're completely wrong. The new method does cover the truth, as it provably does, and it's not much smaller than ignore the machine learning method, and that's good, because it's being honest. It says if the machine learning model is crappy, it's not going to be able to correct the statistical interval very much. It does that automatically. You don't have to ask it to do that. All right, how does this work? So let me just say briefly, I've written this out in the context of M estimation. Okay, so M estimation is estimation where the estimand is defined as the minimum of an expectation of a loss. Okay? And so when you work with M estimation, you take the gradient of the loss, let's call that G, all right? And everything else on the slide is expressed in terms of gradients. So that's good for machine learning people, they like gradients. All right, and so the way this is gonna work is that we're gonna do a little add and subtract. First of all, we have, by definition, the gradient of the expected loss is equal to 0. That defines an M estimator. So we're gonna take that equation and we're gonna add and subtract a term. And when we do so, we're gonna get a term in yellow there, which we can get a point estimate for, all right? And then we get a term in green, which we call the rectifier. And if we were looking just at means, this would be a bias, classically, but in general, we call it a rectifier, all right? And that is a term that we can estimate if we combine the machine learning predictions with the hand-labeled data. So in the AlphaFold case, we had AlphaFold as the machine learning predictions, and for each one of those, we also had some hand-labeled data, 10,000 or 100,000 in the most recent data set from humans. Put those two together, we can get a set-valued estimate of the rectifier. So we can get a confidence interval on the rectifier, okay? That's what's different. We're not just doing bias correction in the classical way. If you have a point estimate, it has bias, you estimate the bias, you add something to cancel the bias. What we're doing is we're taking a confidence interval on the bias creating machinery, and we're taking all the plausible rectifications and adding that to the point estimate. Okay, so it's a somewhat new concept relative to statistical inference. It's related to multiple imputation, but it's not the same. Anyway, you have enough machinery on the slide there to now prove a theorem, which says that if you do this, you form a confidence interval, which is that set valued, the point estimate, minus this set valued rectifier. Then you will form a confidence interval that contains the truth with probability greater than or equal to 1 minus alpha. Okay, so that's not a hard theorem at this point. Okay, so that was my little talk about setting up a principal agent problem, because that was a principal agent problem. The principal was DeepMind, who produced this AlphaFold object, and the agent is the scientist wanting to do something, or vice versa. In fact, probably better to think about the scientist as the principal and DeepMind as the agent. The agent possesses knowledge the scientist doesn't possess. And you can't change what's inside of AlphaFold. You have to work with what it is, all right? And so you've got to interact in a way in which there's uncertainty you can't correct, okay? There's an unknown bias and you don't know what it is. All right, so now let's go for, putting incentives into this picture. So as Ava alluded to, what I really think is most interesting about machine learning meets economics is that incentives come into the picture, okay? So let's, that previous part of the talk didn't have incentives. Let's do that. So this is with Stephen, Michael and Jake at Berkeley and Stanford. Okay, so here's a problem where incentives really do come into play, but it's all implicit. Clinical trials, as you all know, I'm sure several of you have worked on clinical trials, immense investment in all the therapeutic areas. It's sort of tens of millions of dollars a year. And it's because these massive RCTs are being done, and you have to have large numbers of people to have it be trustable. That's all good, but the question is, how do you actually do the data analysis of these clinical trials? And so the FDA is mostly consists of statisticians who are really good at doing false discovery rates and Neyman Pearson testing. And so the cartoon version of what they will do is they'll say, I'm trying to test whether a drug should go on the market or not. Where'd that drug come from? Well, it came from some pharmaceutical company that proposed it. It's a new protein that they've been working on and, blah, blah, blah. They hand it to me and I have to do an RCT on it, which I do. Now, that drug could either be ineffective, let's call that type equals 0, or it could have an effect, a good effect, type 1. Okay, they screen for it being really terrible and killing people. But type 0 just means it's not effectual. And turn this off. And they are good statisticians. So the probability of approval, if it's an ineffectual drug, they set to be less than 0.05. The probability of approval, if it's a good, effective medication, is 0.8. That's the power. And that's the Neyman Pearson test. So it's the optimal protocol from a statistical point of view. And this is not just some linear classifier. This is a very, complicated, probably some deep learning is being used, a very complicated classifier. All right, now is it good, really? Well, not if you bring in the economic incentive story. All right, so consider two cases. One in which there's a small profit to be made. Costs $20 million to run a trial, as you saw. Let's suppose that if you are approved and you go to, you have a license for a year, you make $200 million. Now you can do the little calculation, all the numbers on the page. You can say, well, if counterfactually my drug is not effective, I don't know that, but let's imagine it is not effective, my expected profit will be minus 10 million. All right, and so if I'm the CEO, I'm going to say, do not send candidates to the FDA unless you're quite sure they're good, because we're going to lose money otherwise. That's where the private knowledge is coming into play, because now the inside of the company, they're going to think about it a little bit. They say, well, we know that protein is terrible, let's not send that, but this one seems more promising, let's send that. All right. So that would be great if that's the situation. Most of the drugs coming into the FDA are good ones, and they're doing good statistics, type 1, type 2 error control, and therefore only good drugs go to market. The problem is that we have lots of situations like the one on the right. It costs $20 million to run the trial, but if you are approved, you might make $2 billion, more like ibuprofen or something. Now the CEO can do the calculation, and she might say, counterfactually, theta is equal to 0, what's my expected profit? Now it's easy, you can do the calculation, 80 million. She will now tell everybody in the company, send as many plausible candidates to the FDA as you can. Okay, so, the FDA will have a big job to do, and they will run lots of RCTs, and they will screen them, all right? But now many bad drugs go through that system because you got a false positive rate that's small, 0.05, or it's actually, 0.01, but it's small, but they're sending lots of candidates in, so lots of drugs go on the market. This is really the situation we're in. And after a couple of years go by, people realize that drug is actually not having an effect. More tests are done, and they pull it off, and they put something else in, and supposedly that gets improved. But that couple of years, people, died because they didn't have a good, effective. They thought they had a good medication. It wasn't actually any good. All right. So there's a bit of a cartoon here, but I hope that you'll kind of now agree that some contract theory should be brought into the picture here. All right. So just a one-page primer on contract theory. There was a couple of great talks. Natalie Colina had a great talk on contract theory, so I think all of you know what it is. We've got an agent who possesses private information, maybe their willingness to pay. We've got a principal that wants to get them to do something like come onto my airplane, and they don't know how to set the price. If they knew the willingness to pay, they could set the price. They don't, so they give them a menu of options. And for each one of the options, there's a service and a price. So business class costs this much, economy this much, and so on and so forth. And now everybody gets to see the same menu of options, service, price, service, price. They look at that and they say, I'm going to pick that one because they know their own willingness to pay and they know that's advantageous to them. So they go on and the overall revenue is high and the overall social welfare is high. Okay, so this is the classical theory. As is often the case in these, you look at that and you say, where's the statistics? What if there's a lot of data flowing in and all this is, has to be conditioned on the data? There's not much role for data in this whole theory. They call it Bayesian because there's uncertainty about some things, and they just say, well, there is a probability distribution on that. And let's take averages over that probability distribution. That's it. All right, so we are statisticians, and we want to put statistics into that picture. Oops. So I hope you'll agree that, or you might agree, that this problem really needs a contract theory formulation. The principal is the FDA. The agent is the drug company. And the agent knows things the principal doesn't know, and you want to transact, and you want to do this in a safe way. The difference here is that revenue is not the goal, or even social welfare in any vague sense. The goal here is type 1, type 2 error control. The goal here is to put good drugs on the market. That's a statistical goal, but done in a contract theory formulation. Okay, so we have worked on this, and we've come up with a theory we call statistical contract theory. And just briefly, there's a little protocol. You come in as an agent and you opt in or you opt out. If you opt in, you pay a reservation price R, 20 million, and then you choose a payout function, which is going to be a function of the clinical trial. So it'll be a function of a random variable observed in nature. That's what's new. The menu of options is something we design as statisticians now, and it's a statistical design, okay? I'm gonna show you how we do that in a second here. So we design a menu and someone picks a measurable function out of this menu. They apply that then to the data, which is Z, and that's sampled from P of theta, where theta is the true theta, because that's nature knows true theta. And the RCT gives you a sample out of nature's distribution. Then the agent gets their payoff because they picked the F function, knowing maybe a little bit about what likely Z is going to happen, and the principal gets a utility as well. All right, so long story short, we've done the mathematical theory here. First thing you have to do is write down what you mean by incentive alignment here, and it's pretty straightforward. A contract is incentive aligned if the expectation under the null hypothesis, that's what Z sampled from P of theta naught. Theta naught is the null hypothesis. Under the hypothesis that your drug is not effective, the expectation of the amount you're going to make minus your cost should be less than or equal to 0. Otherwise, you would just make money by playing this game against the FDA. Okay? Setting P less than or equal to 0.05 protocols, which is what's typically done, is not incentive compatible under this definition. All right, now here's an interesting theorem, which is that we were able to prove that a contract is incentive aligned under that definition if and only if all the payoff functions are E values. What is an E value? Well, in modern statistics, this is what we are using nowadays instead of P values. P value is under the null hypothesis, the probability of being greater than some value. It's a tail probability under the null hypothesis. An E value is a random variable whose expectation, non-negative random variable whose expectation is less than or equal to 1 under the null. And in general, it's not just a non-negative random variable, it's a non-negative super martingale. That's the full theory. We know a lot about non-negative super martingales. We know how to design them, we know how to work with them. You can add them, you can put them together. P-values you can't combine, E-values you can. So it's a beautiful statistical object, and the beauty is that if and only if for statistical contracts. If you want to design statistical contracts, you have to be working with E-values, okay? And so, in a longer talk, I would get into some examples, we are back to working with the FDA and also working at companies that are doing this, for example, for third-party sellers, real principal agent problems, trying to design these protocols there. What I want to say one more thing about that is that I also want to be Bayesian in life. So most of the work in machine learning, all this deep learning stuff is all frequentist, and it's kind of frequentist because you're trying to write a piece of software that a lot of people will use. Frequency guarantees over the software. But in real life, especially with, kind of expert knowledge hanging around, where I'm going to work with someone for a year, I'm going to be more Bayesian. I'm going to try to, model things. All right. And so now, what if we do this whole theory I've just alluded to, which was frequentist, and try to do a Bayesian version of that? Something really interesting happens, all right, which is that you can now do Bayesian inference in the principal agent setting without having a prior. And so how does this work? Well, suppose that I'm a principal and I want to do Bayesian inference with some problem, and I can't collect the data myself, I don't have the expertise, but someone else over there, the agent, can and does. All right? They may have a prior, but I don't have the knowledge. They have the knowledge. They have the prior, I don't. All right? What I'm going to do is I'm going to set up a contract for them, which is a list of options, E-values, and prices. And I'm going to give that to them, and they're going to make choices, and those choices will be based on their prior. So I get some knowledge very indirectly by designing a contract in a particular way. I can sort of leak knowledge over, all right? And if I put that in the right equations, I can use that to do Bayesian inference, okay? And so let me just show you briefly how this works. Here's our little protocol. The principal chooses a decision policy, which takes data and goes into, say a classification decision, approve or deny. All right? The agent decides to run a trial at a certain cost, all right, or not, or they might opt out. If they run a trial, they collected the data and they collected the evidence according to nature's distribution, and they give that to the principal. The principal then makes a decision based on the choice of F that this decision policy that they published, all right? And if they make the decision to approve, the agent receives a reward. Okay, so that's the whole protocol, and it definitely is a contract theory sort of protocol, right? If we do the math here now, let's imagine the principal's decision is to thresholding, so it's a classifier. Let's write down the power function, beta of theta. Okay, the probability that x is less than or equal to tau, that's your power. And let's write down an expected profit, which is based on for the agent, so it uses the distribution Q, which is the prior for the agent. The agent could do that, that's their utility, okay? It's their expected reward minus their cost. All right, and now we have a theorem which says, suppose the agent runs a trial, opts into this process, only if this power function, the expected profit, sorry, not the power function, the expected profit is greater than or equal to 0. An incentive story, okay? All right, so now if you do that and you write down the posterior odds that the principal will calculate, it is lower bounded by C, which is a known cost, R, which is this reservation price, tau, which is the threshold that the principal sets, and divided by tau. All numbers the principal easily has access to. And that is now lower bounding the posterior odds, okay? So we are now saying something about the posterior odds. We have a lower bound on the posterior odds. That's an inferential statement that was based on no prior. It's a Bayesian statement based on, you can see it's Bayesian, right? It's probably a theta on the left-hand side. It's a Bayesian statement with no prior. Okay, and economics is giving us that. All right, I think I'm nearly done. How much time do I have? 2 minutes? 2 more minutes. Okay, so the last part of it would, in a longer talk, would be that what I'm most interested in is really trying to take these ideas to governments and say, look, we're going to talk about regulating technology, where data are flowing. We have ideas from statistics, economics, and computer science. We bring them all together. We can tell you a little bit how to think about governance and regulation and market design kind of issues. All right, and a lot of you in the room are working on these kind of things. Let me just say we're really very interested in all this at Berkeley. Here's some of the people that I'm working with. Mina's here in the audience. I think a lot of you know Nika, and then Ali Reza's in the audience as well, and Nivasini's back at Berkeley. So let me just mention one project here that I alluded to earlier with Ali Reza and 2 other colleagues, Ali and Azaraq. This is on these 3 data markets, and I've already introduced it with this slide here. And let me just sort of show you a little bit of the outcome here. If you actually model this 3-layer data market, let's suppose there's just one user. Extensions to multi-users is non-trivial, and that's ongoing work. We have multiple platforms, and then we have data buyer. And if you kind of follow through all the symbols here, you sort of see that there's information flow, that the data buyer wants to infer some regression, and the platform is able to provide a service, which is another regression. And you can make a bunch of linked equations and write down all of the equilibrium conditions here. And we have done that here. And the core of the utility functions are the following. We have revealed information in the revealed sense in economics, that the overall what the user provides to the buyer, and then the buyer's utility is a function of that scaled by some number minus the prices they pay for the data. Okay, so that's kind of the core of the utility story, and I highlight that because this beta parameter turns out to be important. First of all, the analysis is just a generalized Stackelberg game. First of all, platform decides, then user, then platforms, then buyer, and now, there's a theorem, which I won't get into details here, but just to say that this beta parameter gives you a little phase diagram. If beta is too small, then an equilibrium exists and only low-cost companies will enter the market. Low cost means that I don't make enough data on my regular business. I've got to sell data to be in business, okay? And above that, all platforms enter the market. So there's kind of a little diagram you can make as a function of beta, what's going to happen in the market, all right? And now you can look at privacy regulations. Privacy regulations in this case, remember our original story, which is how much noise do you add to the data, okay? And you could say the government could come in and say mandate a certain lower bound of noise. You have to add at least this much noise, or we're not going to let you be in business. Or mandate that you have to be, infinite noise. And so we kind of work through the consequences of those choices here in this model. And let me just sort of say there is a theorem here, and I'm out of time, so I'm going to maybe kind of stop there and leave it there. But you can analyze the GDPR kind of ban on transmitting knowledge and see has that hurt the market? It does hurt the market. You can also go back and analyze user utility, which is what the Europeans supposedly care about, and see, is this hurting the user utility? And the fact, you can pull all that out of this analysis. All right, so that's the kind of thing that we're trying to do, really work with governments here. And let me just leave that last slide up here. Here's some of the other projects that I'm real excited about. One of them, Mina talked about on the first day here, and I just want to mention a couple of others here. One is bringing in experimental design ideas from statistics, which have not been used in either of the fields that I alluded to earlier. And the other is conformal decision theory, which is conformal inference meets decision theory in a multi-agent setting. That's something we're particularly excited about these days. All right, so I'm done. Thanks, Ava, again, for the invite. Thanks for the conference.
I gotta ask, as a fintech guy, and I look at this issue of data regulation as information asymmetry, where we as firms know more about our customers and know more than the regulators. And even in your model, you have to factor in the expected value play, where we look at the costs associated with reputational risk and the probability of getting caught. Yeah. And just what's your thoughts on that?
Yeah, well, so Ali Reza, we have a second paper, which is safety constraints. What if you add the danger that you might get tested? But if you're not tested, you can kind of get through. You add that in as now another constraint. And there are not just qualitative, but quantitative results of assumptions like that. What I want is an engineering field that writes down math and makes models, and then you can point at the model and say, I like this, I don't like this, change and all. I want to do mathematics here. I don't want to just have lawyers come in and make qualitative statements about what you could or shouldn't do based on history. We're in a new era here. Data changes everything. Data is a different kind of good than we've seen in economics. These companies are operating with no control, and it is a different world. And so qualitative arguments in the legal field for the past is not where we should be going right now. So I could go on about this, but I hope you get the flavor. I want to incentivize this audience to sort of say, we are the people that can help formulate the discussion, and we're going to do it with mathematics.